This is Chapter 7, Chemical Reactions and Quantities. Section 8 is mass calculations for chemical reactions. We know from the previous video that the numbers in the chemical equation relate mole quantities of substances that are taking part in the reaction. And this is useful because it scales up and it reflects the underlying molecular or atomic ratio between the substances. The reason it's not that useful, though, is because a mole is a huge number of particles. So it's not reasonable to count out particles or measure moles directly in a chemistry lab. To give you an idea of what I mean when I say it's unreasonable, if you counted one particle every second from the beginning of the universe to today, you would still not be anywhere near having counted a mole of particles. In fact, if you counted 1,000,000 particles from the beginning of the universe every second until now, you would still not have counted a mole of particles. So obviously it is infeasible to think that we can count out a substance, count out individual atoms or molecules to find out molar amounts. So instead we have to fall back onto the molar mass. Okay? So what we're going to do in this video is see how the molar mass allows us to make predictions and relate gram amounts or mass amounts of one substance in a chemical reaction to the mass of another substance in a chemical reaction. And we need to do this by taking the mole to mole ratio, which is at the heart of the chemical equation, but then having mole to mass conversions at the beginning and at the end. So the basic idea is that if we have two substances which are part of a chemical reaction and we want to relate the mass of substance A to the mass of substance B, these are the three steps we have to follow. Okay, first, you have to convert the mass of substance A to moles of substance A by using the molar mass for A. Second, you have to use the chemical equation and the mole to mole ratio between A and B from the balanced chemical equation to relate moles of substance A to moles of substance B. Third, now that you have moles of substance B, you need to use another molar mass conversion, this time the molar mass of B, to convert moles of B to grams of B. Okay, so this is a three-step process. Instead of being able to directly convert mass to mass, we have to understand that the chemical equation is in mole ratios, and therefore, however we're measuring the substance in a lab, we have to first take that measurement and relate it to molar amounts and understand it in terms of the molar amounts. Only then can we use the ratios from the chemical equation to relate one substance to another from the reaction. It'll help if we do an example. So let's take this problem. Suppose we want to determine the mass of ammonia that can be produced from 32 grams of nitrogen gas in the following equation. Okay, so you have the equation here, nitrogen plus hydrogen yields ammonia. Okay, and it's 1 mole of nitrogen plus 3 moles of hydrogen yields 2 moles of ammonia. So we know we have 32 grams of nitrogen from the equation, and we want to relate that to the mass of ammonia. Okay? If this were in terms of moles, then it would be a simple conversion. We would just use the mole to mole factor between nitrogen and ammonia and multiply that by the molar amount. But because it's mass, it takes a little bit more. Okay? So if we're given the mass of one substance in the chemical equation, and we need the mass of another substance, then we'll need the mole to mole factor from the chemical equation, but in addition to that, we're going to need molar masses for those two substances. Okay? So since they're two different substances, they're going to have two different molar masses, and so we'll have to take both into account. Step 2 is then to map out how we're going to do this problem, taking what we're given and calculating what we know. So again, we're given the mass of one substance in the chemical reaction, and we're trying to relate that to the mass of another substance in the chemical reaction. So we're trying to go from here, the nitrogen, to here, the ammonia. But again, we have to remember that the numbers in the chemical equation relate moles. So if we're not directly given moles or asked for moles, then there's going to be other conversions involved. Okay, so in this case, we're dealing with masses, and so we're going to need to use mole to mass conversions, which will obviously involve the molar mass. So the plan here is to start from the mass of nitrogen in grams, use the molar mass of nitrogen to convert that to the number of moles of nitrogen, Then use the mole-to-mole factor from the chemical equation, right? Using the numbers, the coefficients in the chemical equation, remembering that this is a 1 in front of the nitrogen, and use that mole-to-mole factor to relate moles of nitrogen to moles of ammonia. Then once we have moles of ammonia, we need to use another molar mass, this time for ammonia, to calculate the mass of ammonia in grams. So it's a little bit of a complicated procedure, but it will benefit you to take time now to understand what's going on and why each of these steps are necessary. That's because later on we're going to see that there are other types of substances where we don't necessarily want to measure them in terms of their mass, but we might want to measure them in terms of their volume or some other property. But we're still going to need some way to take that measurement and convert it into a number of moles, and then use the mole-to-mole factor from the equation to relate moles. Okay, so this central part of this process is common to many different question types in not only this chapter, but in the following few chapters. Okay, this is again the heart of the chemical reaction, where the equation shows us mole-to-mole relationships. Okay, everything else is contingent on how we're actually measuring the substance. In this case, we're measuring the substance in terms of masses, so we need to use molar masses. Okay, if we were using volume for a gas, for instance, we would need to use some of the gas laws that we'll learn in the next chapter. Okay, so again, it'll be helpful to really think about this entire process, understand it, understand why all of the steps are necessary, not only for this chapter, but for the subsequent chapters as well. That leads us to step 3. Now that we have the plan mapped out, we know that each of those arrows is a conversion factor, and we need to think about that conversion factor. So the first one is converting the mass of nitrogen to moles, and so for that we need the molar mass of nitrogen. Important to point out that since nitrogen is N2, the molar mass of a nitrogen molecule is twice the mass of an individual nitrogen atom. So when you look in the periodic table, you'll see that a single nitrogen atom has an atomic mass of 14.01. For N2, you have 2 nitrogen atoms, and so you need to double it to get 28.02 grams per mole. Okay, and so from that, you have 2 potential conversion factors. We'll see which one to choose in a moment. The second step is to relate the moles to one another. So the mole-to-mole factor from the chemical equation comes from relating moles of nitrogen to moles of ammonia. And again, if there's no number in front, I keep saying it, that means it's actually a 1. So in this equation, 1 mole of nitrogen can produce 2 moles of ammonia. Okay, so that's what this equation down here means. 1 mole of nitrogen gives you 2 moles of ammonia. And so again, you have 2 conversion factor possibilities from that relationship. And then the last one is, at this point, we'll have had the amount of ammonia in moles, and so now we need to convert moles of ammonia to the mass of ammonia, which is what the question is actually asking for. And so now we'll need the molar mass of ammonia. So again, if you look up nitrogen, nitrogen is 14.01, hydrogen is 1.01, there's 3 of them. So add all those together and you'll get 17.04 grams per mole. And that leads to these 2 conversion factors. The last step then is to just set the equation up so that the units cancel out properly, and that will allow us to choose the correct conversion factor from each of those relationships, and then just do the math, multiply everything together. So again, we start from what we're given. Okay, we're given the mass of nitrogen, and we need to multiply it first by a conversion factor, which will cancel the mass of nitrogen and leave moles of nitrogen. Okay, that's the molar mass conversion factor. The second conversion factor will have to cancel moles of nitrogen. So moles of nitrogen will be on the bottom, and it'll have to leave moles of ammonia, the other substance we're looking for. Okay. The third conversion factor will have to cancel moles of ammonia and leave grams of ammonia. Okay, so at this point, grams of ammonia is really the unit that we're looking for. And so this form with all of these units canceling out properly tells us which of each of those conversion factors to use. So for the first, the molar mass conversion factor, we have mass on the bottom and moles on top. So for a molar mass conversion factor, it's always 1 mole, and then the number that you calculate per mole is for the grams. Okay. For the mole-to-mole factor, you just put the coefficient in front of the right substance. So this is ammonia on top, and the number in front of ammonia is a 2, so this becomes a 2. This is nitrogen on the bottom, and so again, that's a 1 in front of nitrogen, so this is a 1 here. And then the last conversion factor is to get from moles of ammonia to grams, and so the moles is going to cancel, and there's always 1 mole for a molar mass, and then the mass that you add up from the periodic table is on top. So you take 32 grams, multiply it by 1 over 28.02, or divide it by 28.02, then multiply it by 2, divide by 1, then multiply it by 17.04, divided by 1. And what you get is 39 grams, keeping in mind that we're restricted with significant figures. So the initial measurement has 2 significant figures. All of the molar amounts are exact because moles are counted numbers, right? You're actually counting numbers of moles, so these are pretty much always exact when they're from relationships like this. And then the molar masses can have as many decimals really as you take from the periodic table. I recommend taking at least 1 or 2 decimals, but in any case, we're still going to be limited by the 2 significant figures from the initial measurement. So our final answer will have 2 significant figures. Let's do another example. This problem says how many grams of oxygen, O2, are needed to produce 45.8 grams of iron 3 oxide in the following reaction. Now we saw this reaction in the previous video where we were dealing with just mole-to-mole factors, and so they told us how many moles of oxygen we had, and they wanted us to predict how many moles of the product we could create. In this case, they're doing that backwards. They know how much of the product we want to create, and they want to know how much of oxygen we need to use. But in addition to that, it also gives us the measurements in grams, and it asks us for our answer in grams. Okay, so we're looking for grams, or the mass of oxygen, based on the mass of the product, iron oxide. So it might be useful for you to go back and compare that problem from the previous video to this problem to see where they're different. The first step is similar, right? We're always looking for what we're given. In this case, we're given the mass of the product, iron oxide, and we're given the balanced chemical equation. We need to calculate the mass of oxygen. So we're relating the amounts of 2 different substances that are taking part in a chemical reaction. Okay, so this is really a key to all of these question types, where we're relating 2 different substances that are part of a chemical reaction. We need the mole-to-mole factor. If we're ever relating 2 substances in a chemical reaction, we're always going to need the mole-to-mole factor from the equation. But because we're not given the moles and we're not asked for the moles, we also need molar masses in order to convert between mass and moles. So we can write a plan. Okay? We start with grams of the product, use the molar mass to figure out how many moles of product that really is, and then the mole-to-mole factor to figure out how many moles of the reactant we need to create that many moles of the product. And then once we know how many moles of the reactant we have, we use the molar mass of that reactant to figure out how many grams of reactant we need. Again, we can go through and develop each of these steps as a conversion factor. So we're looking for a relationship. The first relationship is between moles of the product and the mass of the product. So we'd have to add up 2 iron atoms and 3 oxygen atoms, add up their masses from the periodic table, and we would get 159.70. Okay, so that leads to 2 conversion factors. The mole-to-mole ratio is between moles of oxygen and moles of iron oxide, so we get those numbers from the coefficients in the chemical equation. 3 moles of oxygen gives you 2 moles of iron oxide, so we get these 2 conversion factors. And then the last one is relating moles of oxygen to grams of oxygen. And this is similar to nitrogen. If you look oxygen up on the periodic table, it'll say 16 grams per mole, or probably 15.999, but you can just round that to 16. But a molecule of oxygen contains 2 oxygen atoms. And so we have to double that, and 16 times 2 gives us 32 grams of oxygen per mole. And so we have these 2 possibilities here. Then the final step is to just set the problem up so that the units cancel out in a way that tells you which conversion factor to use at each step. So you start from the mass of iron 3 oxide, which is grams of iron 3 oxide. And so your first conversion factor will have to cancel that unit. Grams of iron oxide will have to cancel. And it'll leave moles of iron oxide. Okay, the first step is converting mass to moles for the one substance. Then the next conversion factor is to relate moles of that substance to moles of the other substance. So that next unit that we are left with, moles of iron oxide, will have to cancel moles of iron oxide, and will leave moles of oxygen. That's allowed us to figure out the related substance in terms of moles, but we still need one more conversion factor to take those moles and convert it to mass. So we take the moles of oxygen up here and we cancel it with moles of oxygen on the bottom of our last conversion factor. And so if moles are on the bottom, this is a molar mass conversion factor, and so we need to leave grams on top, which will give us the correct unit for our answer. Right? The question is asking for grams of oxygen. So once we have these units in the correct places, then we can go in and fill in the numbers. Okay, so for molar masses, you're always dealing with 1 mole of the substance and then the mass associated with that from the periodic table. We calculated it to be 159.70 for this first one. For the mole-to-mole factors, you take the coefficients from in front of the corresponding substance. So you have moles of oxygen on the top, so you take the number from in front of oxygen in the equation, and that's a 3. You have moles of iron oxide in the bottom, and so you take the number in front of iron oxide, and that's a 2. Okay, so that's why it's 3 over 2 instead of 2 over 3. And then the last conversion factor, again, the molar mass always is talking about 1 mole of the substance, and the mass that we determine for an oxygen molecule is 32 grams per mole. Okay, so if you look at it, the first molar mass conversion is going from mass to moles, and so the mass number goes in the bottom. You're dividing by it. In the last step, it's another molar mass conversion, but this time you're going from moles to grams, and so now the mass is on the top and you're multiplying by it. Okay, I don't recommend memorizing that, right? I think it's a much better idea to look at it in terms of how the units are supposed to cancel out and then see where the numbers should go. Okay, but regardless of how you do it, once you have it set up this way, you just take the numbers 45.8 divided by 159.70, multiplied by 3/2, multiplied by 32, and you end up with 13.8 grams of oxygen. Okay? And again, you're limited by the 3 significant figures in your initial measurement. You can take as many digits as you want from the periodic table you're using, and then the mole-to-mole factors is always an exact factor. Okay, so you get 13.8 grams of oxygen. That's answer B. Let's do another example. The reaction between hydrogen and oxygen produces 13.1 grams of water. How many grams of oxygen reacted? So they're telling us the chemical equation, right? We have the balanced chemical equation here. 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water. And they're telling us the mass of the water produced in a particular run of this reaction. So we got 13.1 grams of water. They want to know exactly how much oxygen went into this reaction in order to get out that product. So we're relating 2 substances from the chemical equation. We're relating water and oxygen. So again, let's start by breaking the problem down. We are given the amount of one substance in a chemical equation. Okay, so we're given the amount of water in terms of grams for a balanced chemical equation. And we need the amount of another substance in the chemical equation, right? We need it in terms of grams. So we're going from the amount of water to the amount of oxygen. So once we know that, we should understand that at some point we're going to need to use the ratio between water and oxygen from the chemical equation. We should also understand that because we're given masses, we're going to need molar masses in order to convert from mass to moles. Okay, we need to do that before we can apply the mole-to-mole factor from the equation. And again, we can set up the problem, and it's the same basic outline that we've been doing. Okay. There are a lot of different examples of ways that you can ask this question. You can relate one reactant to another reactant. You can relate one reactant to a product. You can relate a product to a reactant. So there are a lot of different ways that you can interpret it or think about it, right? Are you predicting how much product you make, or are you trying to calculate how much reactant you need? It depends on the situation. But it's always the same basic outline. As long as you're relating 2 substances in the equation, this is the basic idea, as long as you're dealing with masses, I should say. So you start from the mass of the first substance, and you convert 2 moles of the first substance. Then you use the chemical equation to convert moles of the first substance to moles of the second substance, and then you use the second substance's molar mass to convert moles to grams or mass. Okay? So it's the same basic idea that can be shown or seen in a lot of different ways, a lot of different variations. Again, we've seen this before, so the first conversion is mass of water to moles of water, so we'll need the molar mass of water. You can add up the mass of oxygen and 2 hydrogens, and you'll get 18.02. Then we need the mole to mole ratio between water and oxygen directly from the equation. So there's 2 moles of water in the equation and just 1 mole of oxygen in the equation. So you have 2 moles of water equals 1 mole of oxygen, or really 2 moles of water requires 1 mole of oxygen, or something like that. And then the last conversion factor is for oxygen, we need the molar mass of that. And so 1 mole of oxygen, we've seen before, weighs 32 grams. And so this is our third conversion factor, or our third choice of conversion factors. To make the correct choice, we begin to set up the problem starting from our given quantity, the amount of water, and then applying a series of conversion factors where we make the units cancel out in the proper way. Okay, so the first unit is grams of water, so that's the first unit that's got to cancel. That's going to leave us with moles of water, and so that's the second unit that has to cancel. That's going to leave us with moles of oxygen, and so that's the third unit that has to cancel. We cancel moles of oxygen, and then we can be left with grams of oxygen. Okay, so once you've done this a few times, you should get the hang of it, but it's important to just be very conscientious about where you're putting your numbers. Okay, so in this first conversion factor, you have 1 mole on top, and then the molar mass of oxygen on bottom. I'm sorry, the molar mass of water on bottom, 18.02 grams. In the second conversion factor, moles of oxygen is on top, so you take the 1 from in front of oxygen on top, and then moles of water is on the bottom, and so you take the 2 from in front of water for the bottom. In the last conversion factor, you have moles on the bottom, so the 1 goes on the bottom, and then the mass that you calculate for an oxygen molecule goes on top. Okay, and that's again going to leave us with grams of oxygen as our answer unit. So again, you just do all of these calculations and you end up with 11.6 grams of oxygen.